Let's derive Bernoulli's equation here. Essentially what we're saying is if we've got a chunk of water that's here and that water later is here, that the energy it had here is equal to the energy that it has here. This is just straight up conservation of energy, right? And as far as energy goes, we're talking about work plus mgh. This is potential energy. Work is energy, right? Plus kinetic energy. In this situation, right, is equal to the kinetic energy here, or the total energy here, sorry. So work plus mgh plus 1/2 mv squared, okay? Now, as far as mass goes, what we've got is if this is some volume of stuff, right, the mass is just going to be the density times that volume. Now, since we have v's that are velocities and v's that are volume, I'm going to put the little serifs on there, okay? And then as far as work goes, work is tricky, right? Work is force times distance, which in this case is pressure times area. So we got these different areas here, right? Times distance, which spells pad. I like that a lot. And then notice that the area times the distance, if this is the area and this is the distance, that's actually the volume. So work, and we're familiar with this, right? Work is pressure times whatever that volume is there, okay? So if I substitute this for all the m's and I substitute this for the work terms, you end up with pressure 1 times whatever that volume is, right? And this is some incompressible flow. It's also, by the way, laminar flow, so there's no turbulence here. All these things follow these beautiful little streamlines, okay? So for work, I've got pressure 1 times that volume, right? Plus, and then m is density times whatever that volume is, times gh. 1. So h1 is this height here, right? Like that. Plus 1/2. And then again for mass, we're going to put in rho times the volume. Times velocity 1 squared is equal to pressure 2 times, there's my phone. Okay, times the volume plus density times the volume, right? I'm just substituting for the mass, right? So the mass is density times volume times g times h, and this is h2, right? So we got a different height here, right? Plus 1/2, and then again I'm going to put density times volume, right? Times velocity 2 squared. This seems like a lot, but we're just substituting into a fairly well-known formula here, right? If you're paying attention, you can see that there's a volume term that we can cancel out of every single one of these terms. There's a volume factor that we can cancel out. So let's get rid of the volume. This is assuming it's incompressible, right? Okay. And we end up with, this is the final thing. Drum roll, please, right? Pressure 1 plus rho GH1, which you'll recognize as a hydrostatic pressure, right? This is a new thing. So when the fluid moves, it changes the pressure by this much. Right, so this is relates pressure and velocity is equal to pressure 2 plus rho GH2 plus 1/2 rho V2 squared, right? Holy cow. It's not, they don't call it Bernoulli for nothing, okay? So again, this is, in case you couldn't read my handwriting, there it is, right? These all refer to some situation 1, and then there'll be some situation 2 here. Okay, and then the trick is, just like any conservation of energy problem, a lot of these things just are not a problem. Like for example, the pressure is the same, or they happen at the same elevation, so it's only the velocity that changes. And the trick is, looking at the problem going, which terms are 0 and which ones aren't. Okay, in your data packet, this is what they say. So they go 1/2 rho V squared plus rho gz, so z must be our, the only time in the packet, that must be the same as the height, right? And then this is the pressure, and that's constant, okay? Which, sure enough, that's good enough. So that's the derivation, in case you wanted to know where Bernoulli's equation came from.